You know, there's this piece of our energy infrastructure that is absolutely critical, but it's almost completely hidden from view. It's a network that's quietly shaping the future of carbon management, and today we're going to pull back the curtain and take a closer look.
Just think about that for a second. A whole dedicated system, not for cars or trucks, but for transporting captured carbon dioxide, moving it from where it's made to where it can be locked away or reused. The wild part is, this isn't some what-if scenario. It's already here.
That's right. This network of highly specialized pipelines is the literal backbone of our most advanced carbon capture strategies. I mean, without it, the whole system just, well, it wouldn't work. It's the crucial link that makes the entire idea possible.
So what's the mission here? What's it all for? At the end of the day, it's all about creating a bridge, a connection between the problem, which is CO2 emissions, and the potential solutions.
Okay, so let's follow the journey of a single carbon molecule through this system. It's a pretty straightforward three-step process. First, you capture it right at the source, like a factory. Second, and this is our focus today, it gets sent into a pipeline for a long trip. And finally, it arrives at its destination. There, it's either used for something called enhanced oil recovery, or it's stored permanently underground, a process we call CCUS. That pipeline, it's that absolutely vital second step.
And those final destinations are really key. See, this infrastructure isn't just a one-trick pony. It serves two major goals. You've got CCUS, which is all about long-term permanent storage, and then you have EOR, where the CO2 actually helps us get more oil out of old wells. The pipeline network is the common thread that ties both of these massive industries together.
So, how on earth does this all work? Because let me tell you, moving CO2 is not as simple as just pumping it through a pipe. The unique chemistry of carbon dioxide creates a really fascinating and very specific engineering challenge.
And this really gets to the heart of it, right? I mean, from the outside, a pipeline is a pipeline. But a pipe carrying CO2 and one carrying natural gas, they are fundamentally different animals, built to handle completely different states of matter.
The secret sauce here is a concept called the dense phase. To move CO2 efficiently over long distances, you have to compress it, a lot. You squeeze it so hard it enters this really weird state where it's not quite a liquid and it's not really a gas anymore. It's a supercritical fluid, and in this state, you can move massive volumes of it really smoothly.
And to get it into that dense phase, you need pressure. And I mean a ton of it. The absolute minimum pressure inside these pipelines is over 1,000 pounds per square inch. That is an incredible amount of force, and the whole system has to be built to withstand that 24/7.
This chart just lays it out perfectly. Natural gas, it just cruises along as a regular gas at much lower pressures. But CO2, it has to be kept in that special, super pressurized dense phase. That single difference changes everything about how the pipeline is designed, built, and operated.
Okay, so this isn't just theory or science experiments in a lab. This technology is on the ground, operating at a huge scale, right now. So let's take a peek at the real-world network that's already out there.
Get this. In the United States alone, we already have over 5,000 miles of these specialized CO2 pipelines. 5,000 miles. That's enough to stretch from New York City to Los Angeles and almost all the way back again. It makes the U.S. the undisputed world leader in this kind of infrastructure by a long shot.
And of course, there are key players making this all happen. You've got giants like Kinder Morgan, which runs the oldest and biggest CO2 pipeline network out there. And then you have specialists, companies like Bowsher Energy. These are the folks who provide the really critical, hands-on services to get these complex pipelines started up and keep them running safely and efficiently.
And if you want to talk about scale, just look at this number. Kinder Morgan's network, by itself, moves around 50 million tons of CO2 every single year. That is a staggering amount, all flowing quietly underground to oil fields in the Permian Basin.
So that begs the question, right? How do you actually build and maintain something that's capable of handling these kinds of extreme conditions? Let's dive into the nuts and bolts of how it's done.
Well, it really comes down to this three-pronged approach. First, you have to start with the right material, high-strength carbon steel that can take that immense pressure. Then, you protect that steel with specialized coatings to fight off corrosion. And finally, you install a clever system called cathodic protection, which uses a tiny electrical current to stop electrochemical reactions, basically preventing rust.
Now, why all that protection? What's the big deal? The number one enemy of a CO2 pipeline is water, H2O. If even a tiny bit of moisture mixes with the CO2, it forms something called carbonic acid,
And that stuff, it just eats steel for breakfast. So the entire design is basically a fortress, engineered to keep every last drop of water out.
But what about maintaining that crazy high pressure over hundreds and hundreds of miles? That's the job of compressor stations. You'll find them placed at strategic points all along the pipeline. They act like boosters, giving the CO2 a push to make sure it never loses pressure and drops out of that super efficient dense phase.
And all this brings us to one final big thought. As the world keeps trying to figure out what to do about carbon emissions, the importance of this invisible network, it's only going to get bigger. So you have to ask yourself, are we looking at the early days of what could become one of the most critical pieces of global infrastructure in the 21st century? It's definitely something to think about.